I want to make sure we get this.
Okay.
Try speaking again.
Okay, how's this?
Sounds good. Looks good.
That's good.
I'll tell you in a second, but go ahead.
Okay, great. I'll just continue. Okay. Okay, so cool. So with that disclaimer, mentioned this is the title, and this is what I'll be speaking about. So maybe some of this, certainly a few months ago, I wouldn't have really known what was meant by this phrase geometric squeezing, so hopefully by the end of the talk, things will make a little bit more sense. And what's being shown here, this image is actually an absorption image taken from our lab of a Bose-Einstein condensate under rotation. So this is a really old problem in quantum gases, and it's something that we're looking at from a slightly new angle. Okay, so probably in front of this audience, I don't really need to spend so much time motivating why the study of rotation is an interesting and worthwhile thing to do. And so we've heard a lot of beautiful talks on work in liquid helium and in quantum gases on the importance of quantum vortices, and once you have circulation in the system, how that then affects the dynamics. But even without quantum mechanics, if we think about, for example, flows of fluids in a rotating frame, maybe terrestrially, or even astrophysically, when you have fluids flowing around in a rotating system, that can really give rise to some exotic and interesting behavior. And so just to introduce the system that we work with to maybe people who might spend their time in slightly different arenas, we work with cold quantum gases. So generally speaking, we cool something like 1 million atoms down to temperatures of something like a nanokelvin. Okay. This is an image taken from our lab, and what you're actually looking at here is I'll come back to in a lot more detail. This is a vortex lattice in a rotating Bose-Einstein condensate. Okay. The attraction of these cold quantum gases is really twofold. One is that the Hamiltonian is extremely clean and extremely well understood. Okay, so we don't have to make big approximations in trying to figure out what the Hamiltonian describing the system is. And second, from an experimentalist point of view, we have a very, very good handle over almost all aspects of the system behavior. Okay, so we can play around with density and temperature and so forth. We can tune the strength of the interaction between the particles, and we can also apply artificial gauge fields. So we can make these neutral particles behave as if they were charged particles moving in a beam field. And of course, putting a gas into rotation is one nice way of doing that, where they're the Sagnac phase that you pick up if you perform a closed trajectory in a rotating frame. It's completely analogous to the Aronoff-Bowman phase you pick up if you're a charged particle in a beam field. We can use these gases for all kinds of things. Maybe we could use them as a test bed for theory. So some of the work that Martin spoke about yesterday, we're trying to make precise measurements of various hydrodynamic transport coefficients, which are numbers that are really hard to calculate. And so we can go to measure them in our laboratory, and that provides us a benchmark for theorists to measure their theories against. Maybe we can try to realize some of the paradigmatic phases of condensed matter and use some of our complementary tools to learn something about them. And maybe we can even use some of these handles that we have to engineer novel quantum states. Okay, so to engineer states of matter that might not have a direct analog in a condensed matter system. And so the work I'll be talking about today was carried out on a new machine at MIT, and just to keep with the local nomenclature over there, we refer to this machine as Fermi-3. And really the mission statement when we set out to build this was to combine high resolution in situ imaging. So we wanted to be able to take pictures of what these atoms are doing in the track without having to rely on any kind of time of flight or any other probes to see what's going on, and also the ability to project arbitrary potentials with good resolution. Okay, so that was the goal. In terms of long-term directions, we're absolutely interested in looking at the effects of rotation on quantum fluids and maybe trying to use rotation to engineer strong correlations between the particles. So if you can quench the kinetic energy by going to a rotating frame, that's a very, very worthwhile thing to try. And of course, once you're working with these high-resolution systems, that really lends itself to studying the physics of 2D systems. And so we've heard some reports, some really beautiful work on, for example, turbulence in 2 dimensions, where the behavior can be pretty different from its 3D counterparts. In 2D, you also have this nice interplay between BCS physics, where 2 fermions have tried to pair up to form a Cooper pairs, which can then condense and exhibit superfluidity, but also BKT physics, okay, which is the topological phase transition, which mediates superfluidity and reduced dimensions. But normally you might expect increased fluctuations to destroy the order parameter. Okay. And also thinking sort of more in line of what we're doing currently in 3D, but asking how various quantities are transported through the system. So whether that's charge or spin or heat, that's also something that we'd like to see. Okay. So this is really like long-term direction of the machine. And in fact, what I'll be speaking about today was a direction that we never anticipated following. Okay. This is something we sort of stumbled across in the last month or two. And I think it's a nice example of when you have new tools to hand, you apply new tools to a system, that sometimes leads you down roads you don't necessarily expect to find yourself following. Okay, so for anyone who's never built a cold atom machine, this is what it looks like when you do that. So we had the bright idea a couple of years ago to set up a GoPro in our lab. So what you're seeing here is 2 years of work condensed down into about 20 seconds, which makes everything look a little bit more streamlined than it necessarily is at the time. And so what you can see are various people busying around. What we've built here is a lithium-sodium machine. So we have both bosonic sodium and fermionic lithium. This machine is now online, so we started producing degenerate gases around last October. And science-wise, it's really come alive since Christmas or so. This is the machine in action. Almost everything here is sort of superfluous and is just used to get a handle on these atoms. And really all of the action takes place in this glass cell at the center of the machine. Okay. So we prepare our degenerate gases inside this glass cell, and above and below which we have these matched numerical aperture of about 0.5 microscope objectives. Okay. So that's a reasonably high NA, and it gives us pretty good resolution. The sort of ethos of this setup is that we use the top objective to project optical potentials, and we use the bottom objective both to monitor those potentials and also to image our atoms. And just to give you an idea of the kind of detail you can get out, here's a picture of a two-dimensional Bose gas seen through a more conventional imaging system that you find in cold atom machines with the NA of about 0.1 or so. And so here we've taken a BEC, we've squeezed it down to 2 dimensions inside an optical lattice. Okay, and you can certainly see that we have a nice disk of atoms, but maybe it would be hard to pull much information out in situ. But if we look at the same cloud through a microscope, things are a lot more hopeful. Okay, so this is a 2D Bose gas seen from below. We also have lithium now in this system. And of course, whenever you build a machine with arbitrary potential projection, it's mandatory that at some point you write something in the BEC. So this is my token gesture towards that. But this is completely generalizable. You can make any letter that you like. Okay, so once you've built this this setup, of course, you'd like to then test it. And so we asked ourselves what the smallest feature we could try and make in our cloud was, and see how good these microscope objectives work. Okay. Now, if you're working with BECs, the smallest feature that can appear in a BEC is simply given by the healing length. Okay, and that the interaction energy sort of tells you how high a K state is the BEC able to mix into its wave function, and that sort of sets the distance over which the condensate is allowed to vary. Okay. And so a nice object to try and make would be a quantum vortex, okay, where the core size is going to be fixed by the healing length. So what we did is we started with an extremely smooth magnetic trap. Okay, and we place a BEC into this trap. The smoothness is pretty high, actually. We're able to round this out to a residual ellipticity of about 1 part in 10 to the 4. We can then deform our trap into an ellipse. We can rotate it. We can then relax back to a circular trap, and we can take a picture of our cloud. Okay. And sure enough, if we start with an unrotated BEC and subject it to the stirring protocol, so stir it up, relax back to circular, and take a picture, this is what you see. Okay. And so this is a vortex lattice, so an Abrikosov lattice of quantum vortices in our BEC. And I just like to stress this is an in situ image. Okay. So there's no time of flight, there are no tricks. This is simply an absorption image in our trap. Okay. As the vortices form this really beautiful triangular lattice. Obviously, when you see this in the lab, you jump up and down, you're super excited that the last couple of years has really paid off. But you quickly start to wonder. And one question that really bugged us was something that's been bugging people for about 2 decades or so now. And that is, how on earth do you go from this state to this state? Okay. These are 2 topologically distinct wave functions. Okay. This guy is simply connected, and this guy is riddled with these nodes. Okay. And so as an experimentalist, of course, you have the luxury of simply being able to ask the atoms and take a look. And so we decided to stop our sequence somewhere in the middle and take an image of the BEC under rotation. Okay. And what we expected to see was something very disordered, very fragmented. And instead what we saw was this image. Okay. And when you see something like this in the lab, you of course want to try and understand what on earth is going on. And so that's kind of what led us down the story that I'm able to share. Okay. And so if we want to understand what's happening to this BEC, it helps to first really go back to basics. And we're really fortunate in the building we're in, and that right outside the door is a beautiful example of a classical system under rotation, okay, which of course is the Foucault pendulum about 10 yards or so that way. And so this is a pendulum moving in 2D space, so it's effectively a 2D harmonic oscillator. And the generic trajectories of this system, the pendulum bob can perform some elliptical trajectory. Okay, so here's my bob, and it's sort of following this red line. Okay. But if you want to analyze the system under rotation, it's helpful to decompose the motion into motions of different handedness. Okay? And so if our pendulum bob is oscillating back and forth across the plane of the Foucault pendulum, I can understand this motion as simply a superposition of the bob swinging to the left, okay, and the bob swinging to the right. And if the Earth was not rotating, both these motions occur at the same angle of frequency, and so when the bob starts at the top, they then meet again at the opposite side of the circle. Now I can switch on the Earth's rotation. Okay, the effect of that is going to be to downshift the frequency of the left-hand mode and upshift the frequency of the right-hand mode. And so what that means is that if the two bobs were to start at the top, they start moving around, and rather than meeting at the opposite side, one goes a bit faster, okay, and instead meets slightly further around the circumference of the circle. Now, this is this description in terms of this mode decomposition. If you actually looked at the motion of the pendulum bob itself, you would see it follow this curved trajectory. Okay? And this is kind of this, what you see appearing here is nothing more than the Coriolis force, or in the context of B fields, the Lorentz force. Now, the rotation of the Earth is pretty small. It takes a while to notice that things aren't simple back and forth motion. Let's imagine we could turn up the speed of the Earth. Okay? Well, what would happen is that this left-hand mode would become even slower, and this right-hand mode would become even faster. Okay? And in this case, the Lorentz force is so strong that the bob barely has a chance to make it any way around the circumference before it starts to curl back on itself. And now if we leave the video running and allow the system to keep evolving, the motion of the bob is going to be to perform these cyclotron orbits. And so what this can be decomposed as is this slow drift of this leftward node superimposed with this very rapid right-winding circulation. Okay? The net result of this these cyclotron orbits which drift around the circumference of the circle. Now immediately we see that this system has been decomposed into the sum of two separate 1D oscillators, so we immediately know what the form of Hamiltonian will be. Okay? It's simply going to be one oscillator running at the frequency sum, the sum counting the number of quanta in that mode, and there's going to be one oscillator running at the frequency difference. And if we stare a little bit longer, you can put a very physical interpretation on these two modes. Okay, and this slow mode simply sets the center of my cyclotron orbits. This is sometimes referred to as guiding centers, and you might sometimes refer to as the center of mass. But this is the point, capital X, capital Y, around which the bob is then oscillating. Whereas this fast motion here corresponds to some relative motion, psi and eta, okay, and this is the cyclotron motion of psi. Cool, so that's the physical meaning we can pin to each of these oscillators in our Hamiltonian is some oscillator corresponding to relative motion, which is the cyclotron orbits, and some oscillator corresponding to the center of mass motion, which is the drift of these centers. We can then appeal to our understanding of 1D oscillators to tell us something about what these ladder operators constructed from. And we know for a 1D oscillator, the ladder operators are simply built out of the observables corresponding to the coordinates in phase space. This phase space is simply a set of axes where a point in this coordinate system tells you the state of the system. And if I know that point, I can then time evolve forwards or I can time evolve backwards. Okay. Now, for a 1D oscillator that everyone meets when they're first year undergrad, the phase space you're used to could, for example, be the x and p. I need to know the position and I need to know the speed. And sure enough, if you then want to construct ladder operators for the 1D harmonic oscillator, you would build your ladder operator out of these two non-commuting variables. Now the picture is a little bit different here, in that we have these two different oscillators, but the phase space is no longer some x and some p. It's instead the two spatial positions. Okay? And so for my center of mass notion, if I want to define the state of the system, I need to know x and I need to know y. Once I know those two numbers, I then know the evolution of that system. Now, the same goes for the relative motion. I need to know the relative x and the relative y, and again, I can then time evolve my system arbitrarily far. So now my two non-commuting observables that I use to build these ladder operators are not x and p, which I'm used to, but instead the x and the y corresponding to center of mass motion, and the psi and the eta corresponding to the relative motion. And the implication of this is that in a rotating frame, x and y are non-commuting. You can also see that a little bit more directly in that you note that, for example, for the dynamics corresponding to center of mass motion, so the drift centers of these cyclotron orbits, the Hamiltonian describing that system is a function purely of capital X and capital Y, okay, where that drift center is. The Ehrenfest theorem then just tells you the time evolution of X is given by nothing more than the commutator of my Hamiltonian with X. And so if I want to have any non-trivial dynamics, X and Y can be. Cool. So you can be a little bit more exact, and you can actually solve the quantum problem and figure out what the eigenenergies are for the 2D oscillator, 2D harmonic oscillator under rotation. So what's plotted here are the different states labeled by their energy on the y-axis and their LZ, their angular momentum, or canonical angular momentum on the y-axis, on the x-axis. Okay. And what you can see for no rotation, so for rotation frequency 0, these states form this nice fan, because simply the degeneracy of my harmonic oscillator, of course, increases with energy. If I then turn up my rotation, I start to drop the energy of my left-hand modes and increase the energy of my right-hand modes. Okay? And if I go all the way, such that I'm now rotating at the trap frequency, my spectrum splits into the very familiar lambda level. Okay? And so we have these massively degenerate states separated by some cyclotron frequency. And just to put some physical meaning on these states, using this sort of language of guiding centers and cyclotron motion from before, you realize that the different states within a particular lambda level are obtained simply by placing my cyclotron orbits at various points in the plane. Okay? It costs no energy to do that. Okay? Whereas moving between lambda levels corresponds to actually increasing the strength of my cyclotron motion itself. Okay, and I don't want to spend so much time on this slide, but something I'll come back to once you introduce this language of these two non-commuting observables, it very naturally leads you to the language of squeezing, okay, which is something you may more commonly meet when it comes to states of light. Okay. And the rough structure of this analogy is that in the lowest lambda level, for example, I have a set of states labeled by some quantum number. They have some spatial representation, which if I work in the symmetric gauge, which is sort of the natural gauge to use in a rotating system, they simply look like some power of z, where z is just some complex position, x plus iy, multiplied by some Gaussian. And I can move between these states using a ladder operator constructed out of the center of mass x and the center of mass y. That's, of course, completely analogous to the states of light. So if I actually plot the spatial structure of these wave functions, but of course I get these rings at ever-increasing radii from the origin. And this you need when you study, for example, Fock states and states of definite photon number. This time their spatial representation would not be real space, it would be in quadrature space, whereas I project onto some coherent state basis and plot these intensities in some quasi-probability distribution. And this time to move between these states, I of course use my photon, I guess this is an annihilation, but an operator made out of the two quadrature components of my ear. So the basic picture here is this mapping between the behavior of these particles in the lowest lambda level and states of light. And just as I can squeeze uncertainty between different quadrature components of light, or between number and phase, for example, when it comes to rotating systems, I can now squeeze uncertainty between x coordinates and y coordinates. There's this notion of geometric squeezing. It's just the idea that you're not squeezing something in, say, phase space or quadrature space, you're really squeezing spatial coordinates. And let's test this analogy out a little bit with the sort of simplest problem you can consider, which is what happens if I apply uniform force to a particle in a rotating frame. Okay, simply, I have a charge get particle in a B field, or I have a particle in a rotating frame, and I just push it in the x direction. Well, in terms of potential, that corresponds to applying a linear potential whose strength is simply set by the force that I want to apply. Now, x is a terrible variable to try and use in a rotating frame, so I should really rewrite this potential in terms of these A and these B operators, which I've just introduced. Once I have my potential, I can now write down my time evolution operator by exponentiating the Hamiltonian of the system. And what you find is some term containing a load of A's and A daggers. These will simply mix in higher lambda level states. This will generally lead to pretty fast dynamics. And so we imagine coarse graining over that and just looking at this slow drift. Okay? And so the part of this time evolution we're interested in is this term here, which is the exponential of some bunch of prefactors, and then this B plus B dagger. If you recall, B and B dagger are these operators that let you move between states within a lambda level. And if you stare at that for a moment and then you put on your optics hat, you realize that you've seen this operator before, and it's nothing more than the displacement operator from optics. Okay. So in that context, you can imagine starting with, say, the vacuum state of the EM field. And if you wanted then, say, to displace it from the center, you would apply the displacement operator constructed out of the photon of annihilation and creation operators, which would take my vacuum state and it would move it away from the origin. And with this analogy in hand, by simply reading off this prefactor before the operator part in my evolution operator, I can just read off how much do I displace this particle away from the origin. And if you do that, what you find is a displacement simply set by this velocity, just my force over my effective B field times time. And you realize this is nothing more than the Hall drift velocity that you've met before. Okay. So there's no profound conclusion here, but just to check that speaking in this optics language, we can recover this familiar conclusion. So far, that was a little bit of a maybe more theoretical detour. Let's come back to what we actually see in experiments. So what we started off by doing was really the simplest experiment we could think of was simply to rotate our trap at the trapping frequency. Okay, and if you do that, your centrifugal force completely balances your trapping, the force from your trapping potential, and what you're left with is the motion of particles in a uniform plane subject to a synthetic B field. And this is what we see as we let time evolve. So the BEC starts to elongate. Okay, it starts to stretch out and it starts to spill off the screen. So qualitatively, that makes a lot of sense. Now, very naively, our expectation here was, hey, we have an elliptical stirring potential. So in the rotating frame, that looks like a saddle. And so surely these particles then escape along the anti-trap direction. Okay, that makes sense. That, of course, is completely flawed reasoning, and you're neglecting the fact there's a B field. Okay. And in fact, unfortunately, at this point, we didn't have any synchronization with when we took our images. We do have that now. And I can tell you that these atoms actually escape 45 degrees to the axis of your ellipse. Okay, they don't escape along the anti-trap direction, they actually go along the diagonal. And so if you want to try and understand that, let's go back to our math. And so we can write down the Hamiltonian for our system. So we have some kinetic term containing some vector potential, which arises because of working in a rotating frame. This does nothing more than splitting my states into the familiar lambda levels. And then we have the residual, what's left over of our rotation, of our saddle, of our elliptical stirring potential, which of course in the rotating frame simply looks like a saddle potential. So the centrifugal part has balanced out the overall trap. Again, x and y are not very helpful coordinates to use. So let's put this back into the language of A's and B's. And what you again find is a time evolution operator that looks like some fast term, which we'll course grain over. And now you have another evolution, and again, exponential of some prefactor, and this time b dagger plus bb. Okay. And of course, again, putting on your optics hat, you stare at this for a moment, and you realize this is simply a squeezing operator. Okay. And if we now, this is just simply, in the quantum optics language, starting with a vacuum state and applying a squeezing operator, this time with an imaginary squeezing coefficient, okay, with this I at the front, and what it leads to in an optics language is exactly squeezing along the diagonal. That's a slightly mathematical argument. You can be a bit more physical. If you just ask yourself, what does the saddle potential look like in the rotating frame? You can draw these isopotential lines, and then you remember from classical physics that if I have a charged particle in a B field and I apply some force, what I get is a drift of the cyclotron orbits perpendicular to my force. Okay. Now, another way to restate that is that my cyclotron orbits will drift along isopotential lines. Okay. So you immediately see that a bunch of particles starting off at the center of our trap will start to escape along the diagonal. Okay. So they'll still perform a cyclotron motion, but the center of that orbit itself will move off along the diagonal. Okay. You can also check for yourself that the velocity field generated by this flow is irrotation. Okay, and so this squeezing, which we just referred to, this is squeezing. You can ask, what are we squeezing? Okay, so going back to the operator, what you're squeezing are the two observables which make up these ladder operators B. Okay, and there, if you remember, they are x and y at the center of the cyclotron orbits. Okay, so what we're doing is we're squeezing down the uncertainty in one direction, and we're getting growth of the uncertainty in the other. Okay, so we're squeezing down the center of the orbits, but we're not squeezing down the cyclotron motion itself. So the actual orbit itself will still continue. And then you realize in this language, the wave functions in the lowest lambda level, and for example, in the Landau gauge, which is something that, again, you derive in undergrad, which are these infinitely extended strips in one direction. What that corresponds to is an infinitely squeezed center of mass coordinate. So there's infinite uncertainty in one axis and zero in the other, but I'm still left with the positional uncertainty arising from the cyclotron motion itself. Okay. And so what we ought to see as our cloud gets squeezed is that the thickness of the cloud shrinks, and eventually it should stick at a width set by the cyclotron motion. So what we can do is we can simply read off, you can take a fit the cloud across its profile and ask what is the thickness of this cloud as a function of time. Okay. And what you indeed see if you look at the Gaussian width of the cloud in units of the magnetic length against time, is that this width starts off at some higher value, which we set by the interactions and so forth. It decays down, eventually it plateaus out to, in this case, twice the magnetic length. So what you're seeing here is that the center of mass motion has been squeezed down to a line, but I'm left at the smearing due to the cyclotron motion itself. We can also ask about the Hall current itself. The math is not so bad, it's a couple of lines. We know that we're applying some saddle potential to the atoms. So that saddle potential applies an azimuthal force, which is radially dependent. Okay. So I can ask what that azimuthal force is as a function of radius. That's an easy derivative to do. Once I know my force, if I have an azimuthal force, I get a radial Hall drift. Okay. So once I have my force, I can work out my Hall drift. You can put everything together, and you come to the conclusion that the density of the atoms at the center of my trap ought to drop exponentially. Okay. And it should drop with a time scale set by the strength of my synthetic B field and the strength of my saddle potential. And so what's shown here is the density of the cloud at the trap center against hold time. And what you indeed see is this pretty much exponential decay. It's still fairly preliminary data. The fitted time constant here is about 60 milliseconds, and just this naive argument gives you about 50. Okay. So we get reasonably close, but this is still something we'll work on. And just one final point I'd like to make is you can also ask, as well as the width, but what should the profile of this trap look like, of this cloud look like? Well, we know that when many lambda levels are occupied, so when our chemical potential is much bigger than my cyclotron frequency, I can mix a lot of different wave functions into my BC wave function, and the cloud will adopt the familiar Thomas Fermi profile, which you're used to from non-rotating gases. And indeed, at early times, if we try to fit our density profile with a Gaussian, which is this black line, you can see that it's really failing down at the low densities and up at these high densities. And in fact, this red profile will be fit a lot better by Thomas Fermi. But as the cloud stretches out, the chemical potential drops. At some point, that falls to less than your cyclotron frequency. Your VC now lives in the lowest lambda level, and the only states it has available to it there look like Gaussians of the width set by the magnetic length. Okay, so however you combine those together, it's tough to make anything other than a Gaussian wave packet. And indeed, at long times, what you see is this very good fit by a Gaussian. Okay, so far that's nice, and it's something we're quite excited about. Still very much trying to figure out, but it doesn't tell us anything about how circulation enters the system. So certainly the squeezing is never going to give us vortices in the gas. And so in order to figure out how you go from this unrotated BC to this vortex lattice, again, we're experimentalists, so we can ask the atoms what happens. And so I can show here some movies for BC under rotation at different rotation frequencies. And just to give you a rough idea of what to look for, which I can say before I start playing, what you'll see is that the BC will elongate, it will then start to twist itself into almost a galaxy-like spiral. Okay, and then you see vortices start to appear between the BC and the arms of the spiral. So some of it depends a little bit on the color scheme you show. This is rotating at about 75% of the trap frequency. You see these very faint spiral arms developing. And then later time, you start to see vortices appearing at the edge of the BC, which then diffuse into the bulk until what you're left with is a liquid of vortices. We need to, if we apply a little bit of cooling and let the system find its ground state, this vortex liquid would then crystallize into a vortex lattice. We can stir a little bit faster. This time, this twisting into the S becomes a bit more apparent. And again, you see this nodal line remaining along the edge of the condensate, along which vortices start to appear and then diffuse into the bulk. And then just finally, I'd like to show if you stir just a couple of % below the trap frequency, you get a really qualitatively different behavior, where the BC stretches out and then actually will fragment. These little remnants will then further fragment, and what you see is this gradual breakup of the condensate from all of the angular momentum being carried by this large-scale flows until what you're left with is an extremely unstructured liquid of vortices. This is not a thermal cloud. I mean, if you look at this thing, it's really riddled with holes in the density profile, so it's really full of vortices. It's something we'd like to spend some time on, but I actually won't talk any more about this today. But hopefully in the future we'll have some more stuff. Okay, and so when you see pictures like this, so this cloud stretching out, and then when it goes one way, it starts to curl to the left, and when it goes this way, it starts to curl to the right. You know, if you forget that you're looking at, say, a stirred BEC, and think about, for example, the flow of particles, charged gases in a B field, for example, this really starts to look like edge states. Okay? And we can make the analogy a little bit more explicit by making our own edge states. Okay? And so we can do an experiment where we make one of our strips where the particles are flowing out radially from the center of the trap, and then we simply turn on a wall potential. Okay, so a very sharp green light. And when you do that, what you find is that when the atoms are flowing out to hit the wall here, they start to curl to the right. And likewise, the atoms flowing out this way, when they hit the wall, they start to curl to the right. Okay, and so you map from this radial flow onto these edge states. And you can understand this a whole heap of different ways. You can imagine that these particles, again, are simply following isopotentials. Okay? Now it's the isopotential saddle plus this green wall. Okay? You could also imagine that the green wall is applying a force radially, therefore you get an azimuthal drift velocity. Okay? And whichever language you want to use, the conclusion ends up being the same. Okay, but the sort of similarity between these got us wondering, in this case, we've somehow optically induced these chiral edge states. So we've sent in a potential and we've persuaded these atoms to start to twist themselves. Okay, maybe something similar is going on here. This time is that the interaction is actually self-inducing. Okay, so we were curious to see how far this sort of language of optics could take us in understanding the evolution. And so just to remind you of the rough evolution we see, we start with our unrotated BEC. We set it rotating, the thing starts to stretch out along the diagonal. And then this BC then begins to twist itself into a spiral. Okay, you can see there's this nodal line along the edge of the condensate. And then eventually, I don't know how clear it is, but what you might see are 3 vortices, 1, 2, 3, and then 1, 2, 3. So vortices begin to appear along the edge of this condensate, which these spiral arms will actually grab. Okay. And so now it turns out, as we're discovering, I guess this has been known for a while, but trying to include interactions in a Landau level picture is a pretty difficult thing to do. So you're working with these macroscopically degenerate manifolds of states. And so, how on earth do you, somehow these interactions then either split the degeneracy, okay, but figuring out exactly how that happens is pretty tough. So we've really taken the simplest of 0th order argument you could make, just to at least qualitatively see how far we can get. Okay. And so the simplest way we could think of to include the interactions is simply to include them as a mean field potential. Okay. We simply say that the atoms feel a potential proportional to the local density. So again, to 0th order, the cloud is circularly symmetric, so we can expand this mean field potential in even powers of the radius. You can check for yourself, or just realize that the constant in the quadratic term can't do anything interesting. Okay? The constant just gives a constant shift to everything. A harmonic potential means that you have a radial force that varies linearly with radius. Okay? That then means you have an azimuthal velocity that's linear with radius, and that just corresponds to rotation of the entire sample. Okay? The first term that can give you any twisting is this chap, okay? this article 4. Okay, so again, making the simplest argument we can note that the radius of the nth state, so in the symmetric gauge, would be the nth ring-like wave function, or in the language of optics, it would be the nth Fock state, goes like root n. Okay, and therefore the nth state should simply pick up an extra phase, which goes like n squared. Okay. And so again, putting on our optics hat, we realize this operator is nothing more than the Kerr nonlinearity. Okay. And this is something that occurs in media where the refractive index is actually modified by the intensity of the light that's propagating through. So we simply asked ourselves for fun, how much of this physics can we capture by imagining the evolution of a photon state under both squeezing, okay, and also under this Kerr nonlinearity. And this is what you see. I mean, even to call it a simulation is too much. This is an analytic expression of how this thing evolves. It's a one-line thing in Mathematica. And what you indeed see is this thing start to twist, start to squeeze, and start to elongate, and then twist. These spiral arms developing, and then vortices appearing between the main body and the spiral arms. Okay. So we thought it was, we're not claiming this is quantitatively capturing what's happening, but we thought it was pretty neat, at least qualitatively, how much of this behavior is captured within this coherent language of optics. Okay. There are many directions which we're pursuing and want to pursue. So this is sort of necessarily a very, very brief and restricted outlook, just to give you an idea of the kind of things which we're currently trying in the lab. When you figure out that you can understand quite a lot of this evolution within this very coherent language, one of the natural questions is to what extent this is a reversible process. And so one can imagine playing tricks with, for example, flipping signs of your saddle potential to actually see how far can I start to wind up my BC and then maybe actually start to unwind it. And at what point does that reversibility break down? And once you've cast things in the language of this optics and these various squeezing operators, one could also imagine actually sculpting sort of custom squeezing operators. So can we send in nicely crafted optical potentials, which maybe imprint desired flow patterns on condensate? Well, of course, we now have this tool of being able to image these vortices in situ. That, of course, lends itself to a whole host of different experiments. One of the first things we tried is looking at the evolution of this vortex lattice at increased rotation frequency. So what happens if we make a lattice and then we ramp up the rotation rate of our trap? So what I'm showing over here is the vortex lattice in real space and in Fourier space as a function of some, unfortunately, unnormalized, what we call whir frequency. So down at relatively low rotation frequencies, something like 80% of the trap, you see this nicely structured abricosal lattice. And then in Fourier space, that long-range crystal structure is revealed by this nice six-fold symmetric peaks in Fourier space. And then as we increase the rotation rate of our gas, what you see are these peaks, the contrast of these peaks vanish. What that corresponds to is a melting of this vortex lattice. Okay. So it turns out it's actually pretty difficult to stir this thing up without melting the lattice. And so we've had some nice discussions with Tapio Simula about this. We think what's going on here is that the Kachenko modes corresponding to phonons propagating through the crystal of vortices become so soft as you get close to the lowest Landau level. It becomes extremely difficult for them not to melt this. So one of the things we're currently trying to pursue are maybe slightly less destructive ways of adding angular momentum. Something else we'd like to check, which we think would just be a pretty cute mathematical consequence of being in the lowest Landau level, is that if the only wave functions you have to build your wave function from look like some power of z multiplied by some Gaussian, okay, then no matter how you combine these wave functions, okay, what you're left with is some complicated polynomial, again with the Gaussian at the front. The fundamental theorem of algebra then tells you that any polynomial can be written as a product over its roots. And the consequence of this is that in the lowest Landau level, the position of the vortices completely determines the density profile of the gas. And that once you have in situ imaging, that's something that you can actually directly check. And then just as a final comment, something I always grew up learning was that the size of a vortex is set by the Healing length of my condensate. Again, the argument there is that it's the interactions that are mixing in higher K states to my wave function, and that's telling me what's the length scale over which things can vary. But as I get close to the lowest Landau level, that's going to start to break down. Okay, once my chemical potential is less than my cyclotron frequency, the only wave functions I have to play with are Gaussian wave packets of the width set by the magnetic length. Okay, so what you should expect to see is actually a crossover where the vortex core size moves from this interaction set healing length instead to the magnetic length. Okay, and again, being able to look in situ is a very nice handle to see that happen. So with that, I'd like to wrap up and thank everyone for listening. I'd also like to really acknowledge the fantastic group we have over at MIT. So the students, Bishrup, Harth, and Zenji, so these guys are the more senior students. They've been sort of splitting their time working in a superposition of both running these experiments on the 3D uniform unitary gas, so for example, the first and second sound experiments Martin spoke about yesterday, but also involved in setting up the new labs. They've been busy. And Elia and Cedric are the two younger students, and they've been working on setting up this new machine. Of course, fearless leader, Martin, and also the general extended group, the whole CUA community, and various people who've spent various amounts of time with us over the last few years. So thank you very much.
Questions? Aaron?
I was wondering if you can do this experiment in the box trap and considering transverse direction very flat.
Yeah.
Potentially.
Yeah.
That would be an interesting thing to see how it will develop. But that I think will be qualitatively different.
Yeah. So we have we actually, so I guess the only place that appeared in the talk was where we intentionally made these edge states by flashing on a wall. We do have a very sharp circular optical potential. So, I mean, probably maybe even today in the lab, people are trying to get that to work. But yeah, we'd like to try and see this evolution when you have a hard boundary, and also see like what does the structure of this vortex lattice look like once you impose that boundary condition. Okay, that's absolutely something we want.
So in that integral sign shape of the condensate, you see all the vortices at the boundaries.
Yeah.
Hydrodynamically, you would say that there's an instability nucleation barrier. It takes a long time before the vortices enter the cloud, and it's a really tough problem to figure out what is the time scale for going from that state into the vortex field.
Yeah, so there's the breakup between this.
But in your one line of mathematical code, you should have analytically a time scale. Can you pull up a time scale for it? You can see when the vortices enter in that, and can you maybe try to get an insight on the time scales of the creation process?
Yeah, absolutely. Yeah.
Cool. Yeah.
I was wondering, so I don't really know so much about the level stuff, but I recall one of the things that made it difficult in PECs was that you were sort of looking for a limit of sort of like 4 particles per vortex or something like that. Like this extremely high rotation. And so, I mean, here you end up with, so your centrifugal force kind of flattens out the potential and the density goes way down.
Yeah.
Is it necessarily saying that you are in that limit?
Okay, yeah, so thank you for the question. That's a very important question. So for fermions, the situation is a little bit simpler. You're either lowest lambda level, which corresponds to filling fraction toward unity, or you have many lambda levels and your filling fraction is large. With bosons, there's an intermediate regime. People sometimes call it the mean field lowest lambda level regime. Your chemical potential is less than the split between your levels. But still, the number of particles per vortex is still much bigger than unity. Okay. So you can imagine then everyone is living in the lowest lambda level, but my number of particles per state in the lowest lambda level is still high. Okay. And so the fact that bosons don't have Pauli exclusion lets you access that. So you're not necessarily hitting like fractional quantum Hall type behavior, but still the behavior is very different from kind of full mean field where you have many lambda levels and your ratio of particles to vortices is high. So it's a perhaps experimentally slightly more accessible regime that bosons gives you. I don't want to say never when it comes to
even integer quantum Hall. Yeah, as you said, I thought that to see the integer quantum Hall effect, the plateau in equivalent plateau of resistivity, you need to be in a regime where you have pair vortex. You know, how many magnetic lines do you have in your box?
Yeah,
so how many atoms do you have per flux line?
So the number exactly. So the number of atoms per flux line is still hundreds. Okay, so it's your filling fraction is still very large. Okay, but you can still have your chemical potential with everything little. But I don't claim at all that we're near unity filling fraction. That's not.
So it's not yet in quantum Hall regime.
It's not yet. Yeah.
I would say quantum Hall physics is the physics of the lowest lambda level. There can be an interest in studying this mean field regime. And for example, this 1D strip, it's actually beautiful 1D Bose gas, realized in a very different way from what people usually do. So it is quantum Hall physics. It is not integer quantum Hall like the plateau of resistivity physics, right? You had a question.
Yeah. So I had a question about the mean field. So is your B and C coefficient negative? I would expect that the interaction would get weaker as you go.
Yeah.
The result depends on the time.
Sure. I don't. Yeah. What? Yeah. Absolutely. I guess the take-home message there is completely qualitative. It's just that any deviation from quadratic profile. So, for example, any deviation from your Thomas Fermi profile, which would occur just at the edges, is enough to start to twist itself. Okay. So our thinking is maybe that as soon as, even at the edge, even if there's a small deviation from perfect quadratic behavior, that's already enough to start to drag the edges of this thing around. So the development of the spiral, you can understand as like a self-induced twisting. Yeah, in terms of the A's and B's. Yeah.
So all this physics for the twisting up to this graph should be reversible.
Yeah.
So
Yeah.
can you unwind all this structure?
So I think you may need a flashback resonance to do that, because if this twisting is arising from the interactions of the particles, what you'd like to be able to do is flip the strength. So yes, it's tough as so.
In principle, you could reconstruct.
You can imagine playing a lot of cool tricks, for example, with the without the interactions. Just the saddle potential gives you this radial Hall current. You could certainly imagine, say, suddenly jumping your saddle by pi_4 and then driving this flow back towards the center. So the state you produce there it's not clear what that should be. We'd like to play with that. Yeah. And also, I mean, I sort of mentioned that you can sort of discard this admixture of higher lambda level states in the time evolution. The argument there is that your Hamiltonian is static, okay, and so you're trying to connect your state to some much higher energy states. So it's a little bit like some DC Stark shift or something. But if you could then apply some, say, some oscillatory perturbation to the strength of your saddle, you could then actually coherently mix in contributions from high lambda levels. So I think in terms of unwinding this, that's tough without a flashback resonance, but in terms of doing some cool stuff with time dependence of various squeezing operators, anything you can do with the magnetic potential, you can reverse time.
Good. Oh, Michael. Yeah.
How many atoms are in there? Roughly?
500,000.
Good question.
Yeah. What about you?
Okay, Christophe. Yeah.
Okay, last. So yeah. How 1D is your BEC?
It's 1D in the sense that you've frozen out all of the transverse motion and you occupy a single lambda gauge wave.
Could you directly prove the 1D character of the DC by studying the fluctuations?
Sound.
Yeah, we'd like to. So we've already again
make a local perturbation.
Absolutely, yeah, totally. Yeah. So already, I mean, seeing these edge states return on this wall, and you see this collection of particles. We already see if you do that violently, you see some sound propagating in this thing. So there's nothing like methodical yet, but again, that's on our list, our growing list.
Nearly.
Awesome. So you said that you can unwind this one. Can you actually pinpoint to the moment when it's no longer reversible?
Okay. I say that I can't unwind this without a flashback resonance.
No, you could.
But yeah, if you could, then I mean, can I point to it now?
No. Like at what time?
I'd love to do that. I'd love to do that. Yeah, and I think like really what surprised us is how far coherent evolution gets you.
No, but I mean, what moment do you know? Oh, now I can't anymore.
We try it and see if you get back to it.
We just replace our oven with potassium 39 and just do it. That was a joke to the helium community. It's difficult to change the species. With that, let's thank Richard for a wonderful talk.